Hi, I'm Mike Stanzik, and welcome to Digital Electronics Classroom. In this video, we're going to be looking at deriving the series rules from Kirchhoff's laws and Ohm's law. And this is a simpler model in which we don't have to do the full Kirchhoff's laws and Ohm's law in the analysis of our series circuit. So these are rules that apply to series circuits only, and because of that, they're a little bit of a simpler model. So let's get started. Series rules. So let's go ahead and draw a series circuit right here. And I want to label some things. We got V0 right here. Got R1. R2, and then we also have the direction of our currents going this way, like so. I also want to label our nodes. So we have node A, node B, and node C. So there we go. And so what does the series rule say? So, well, first off, we have to know what a series circuit is. And so we say that two elements are in series. If there are no splits or junctions between them. So we can see in our example here that resistors R1 and R2 in series because in the node B there are no splits or junctions, so it goes straight through from resistor 1 to resistor 2. We can even follow that along through the element and through node C to get back to the battery. And so resistor 1 and the battery are in series, even looking at the path that goes through resistor 2. So you could go through an element and still be in series with something, as long as there's no splits or junctions in between the element you're looking at and the other element that you're considering to be in series. So we're going to look at KCL, KVL, and Ohm's law and see how this derives expressions for voltage, current, and resistance that we can use for this model. So let's start out with KCL. So KCL looks at the currents, and it says that the currents into a node are equal to the currents that are out of the node. So if we look at node A, we look at the currents coming in, we can see we have this current, I0, coming into the node, and we have this current, I1, leaving the node. So I0 equals I1. If we look at node B, we have I1 entering the node, and we have I2 leaving the node. So we have I1 equals I2. And if we look at node C, we have I2 entering the node, and we have I0 leaving the node. So I2 equals I0. So we can see that all of the currents are equal to each other. I1 is I0 is I2, and I2 is I0 as well. So they're all equal to each other. So we can come up with our first rule is that currents are equal. I just wanted to see if that would work. I guess it didn't work as well as I wanted it to. That's okay. Currents are equal to each other. That's our first rule. Now let's look at KVL. So in KVL, we know that the rises are equal to drops as we do go around the loop. And so we're going to go around the loop in this direction. And so I can start at node C, and I can look, we go from minus to plus, so this is a rise of V0, and then I go from plus to minus, that's a drop of V1, and then plus to minus through R2, that's another drop. And there's only one loop here. So our expression says that V0 equals V1 plus V2. And so we can see here that the relationship is that the voltages add. I'm not going to do that special thing this time, we'll just leave it as it is. So great, so there we have it. Let's continue to move on. And I want to now look at resistance. And for resistance, we're going to add in Ohm's law. And for Ohm's law, we're going to start with this expression from KVL. So V naught is equal to V1 plus V2. And then in this case, I'm going to use Ohm's law to substitute as V is, oops, I'm sorry, no, V is I times R, not I over R. So V is I times R. Great, and so then we'll substitute into for each of these V's. And so we have I0 R0 equals I1 R1 plus I2 R2. The other thing we know here is that I0 equals I1 equals I2. So we can just call this just some general I and divide by I. So I'm going to divide by each of these. And so since there's a term, and so each term has an I, that means that it'll drop out and we'll end up with this expression. R0 equals R1 plus R2. So we can see that the relationship here is that resistances add. And that's why when we add a resistor in series, the overall resistance gets larger for that circuit. And that's what we're seeing here when we do those resistances add. This isn't actually, though, the resistance of the battery. So if I go back up here and take a look, this isn't R0, the resistance of the battery. It's actually the resistance of the rest of the circuit, or what we call an equivalent resistance. And so I want to talk about that just a little bit. So I'm going to go ahead and talk about this as being not R0, but equivalent resistance. And we'll give a definition here for equivalent resistance. It's the value of one resistor that would draw the same response and this is the current from the battery as the original circuit. Okay, so I'm going to draw a couple pictures here to show us show you what I mean by that. So if you need a second to pause the video to write that down, go ahead and do that. But I want to kind of go back up to the top here and take a look at the original circuit and then draw a couple pictures here to represent the original circuit and then the equivalent circuit. So here's our original circuit. And I broke it up into two parts. This is R1 and R2. Let me just get rid of, actually, I'm going to draw it up here. Let's get rid of some of this. run into my picture-in-picture. Okay. So here is the original circuit. Ugh. Pardon me. We'll get there. Great. And there's R1 and R2. So I kind of think about this as one sort of box, right? So imagine that it's a black box. We don't know really what's inside of it, even though we do right here. So when I connect this thing to the voltage V0, what happens is that it causes the current to flow. So there is no current through this battery until we connect the rest of the circuit to it. And then when we connect the rest of the circuit to it, we get a flow here, I0, and that I0 is dependent upon what this rest of the circuit looks like. So what equivalent resistance says is that, okay, well, if you connected a different black box, and that black box happened to have one resistor in it, and that resistor happened to have a value that was the sum of these two resistors, that it would draw the same exact current I0. So from the outside, we wouldn't be able to tell the difference. So we can't tell the difference. Although they are different. And so since they are different, they aren't equal to each other. But since we can't tell the difference and the behavior is the same for both of these circuits, we say they're equivalent. And so that's where the sense of equivalence comes about. Equivalent, not equal. And so this resistance value, R1 plus R2, is what we call the equivalent resistance. So I hope that's helpful for you of understanding a little bit better about what equivalent resistance is. Let's look at one more thing, and that is power. So power is V times I. We said that the I's are all the same and the V's add up. So these ones add. These ones are the same. So it's going to be equal to I times V1 plus V2. Okay, so this is V naught times I naught, right? And so if I distribute that, I get V1 times I, and since I and I1 are the same, it's just I1, and V2 times I, and since I and I2 are the same, it's just I2. So we can see this is P1 plus P2. So P0 is P1 plus P2, or powers add. This makes sense because of conservation of energy. Whatever power is added to the circuit by the battery must be, it can't just go nowhere, so it has to be transformed in some way, so it's received by the elements of the circuit, in this case the two resistors. So if we add up the power received by the two resistors, they would equal the power that was entered into the circuit by the battery. Well, I hope this was valuable to you and you understand a little bit about where these series rules come from. Let's just recap of what we got. So we said that in series we have the currents are all equal to each other, the voltages add up, the resistances add up, and the powers add up. And those are our 4 rules for series circuits. Thanks for watching. I'm Mike Stanzik. This is Digital Electronics Classroom. And until next time, have a wonderful day.